Good morning, this is your Stat Sensei, Mr. Spensei, and this is a video on the chi-squared death packet. So this is problems, this is a death packet for chi-squared and regression. We'll be focusing on chi-squared and we'll be doing problems 101 through 110. So a round spinner is divided into 5 sections where the sections do not have the same size. All right. Using the measure of the interior angles, the probability of the spinning landing on any individual space on the spin is calculated and given in the table. So we have 40%, 20%, 20%, 15, and 5. That should add up to one whole. A statistics student is asked to test the integrity of the spinner using a chi-squared goodness of fit. What is the minimum number of times the spinner must be spun to conduct this test? Well, basically, they're saying, hey, we have what are my conditions? Well, I have to have a random sample. Okay, N has to be less than 10% of the population. And the third condition, the expected value has to be greater than or equal to 5. The expected value has to be greater than or equal to 5 for all cases. All right, so let's do that. We have to take the worst case. So I'm going to take 40%. And I'm going to go, well, 5 divided by 0.4. So this tells me this would need 12.5 spins. All right. I take 5 and divide it by 0.2 and tells me, oh, this would need, excuse me, I divided that by the wrong number. 5 divided by 0.2. And I get 25. This needs 25 spins. Well, this is the same, so it's also going to be 25 spins. Then I'm going to have 5 divided by 0.15. That's 33 spins. And then I come to this one and I go 5 divided by 0.05 and I get 100. All right. I have to always take the worst case scenario. The worst case scenario is 100. So I would need 100 spins. So basically, you're going to take your expected value that you have to have is 5 and divide it by the percentage. All right. 5 divided by whatever the percentage is. And so 5 divided by 0.4, 5 divided by 0.2. And the worst case is 5 divided by 0.05, and that equaled 100. All right, on to number 102. A geneticist claims that 4 species of fruit flies should appear in the ratio of 1, 3, 3, 9. Suppose that a sample of 480 flies contains the following. 25, 92, 68, and 200 and 295 flies. All right. Does a chi-square test show sufficient evidence to reject? All right, this is a tricky problem. All right. First off, let's add up these values. So 1 plus 3 is 4, plus 3 is 7, plus 9 is 16. Let me do that, show you real quickly. All right, all I did was just go 1 plus 3 plus 3 plus 9. That gives me 16. I just added up these values. We're going to need that. And then they told me these values add up to 480, so I'm going to trust that. So it looks like we have a total of 480. And that's my sample size. So we're going to go ahead and set up our chi-square test. We're going to go to stat edit. And we're going to input our data. Our observed values in L1, 25, 92, 68, and 295. 95, or excuse me, 25, 92, 68, and 295. Then I'm going to put in the 1 enter, 3 enter, 3 enter, 9 enter. But what I really need is a percent. So I need to divide these blue 2 divided by that total of 16. So now I have percentages, but I need my expected value. Remember, expected value is N times P, the sample size times the percentage. So I need to multiply all those percentages by 280 or 480, excuse me. So blue 2 times 480 And there's my expected values. Okay, so now I have my expected values, and so I can run the test. So stat test chi-squared gof, L1, L2. How many categories do we have? One, two, three, four. So that means we have four minus one. Categories minus one gives us our degrees of freedom. So four minus one. And let's look at this real quickly. One other thing we need to do is um, they're claiming that it is in this ratio. So the hoe is equals the ratio. The ha is at least one does not. So at least one does not equal that ratio. Okay. So let's find out if we have a p-value, if it we reject this if we have a small p-value. So let's see what happens. All right, I have a 0.0355. They did not tell me what my alpha is. If they don't tell you what your alpha is, we use a 0.05. All right. So the it was so this means we get to reject this and believe that there's at least one different. All right. Because my p-value is 0.035. Kind of running out of room. Let me get a separate sheet of paper. So we ended up with a p-value of 0.0355. We have an alpha. They didn't give us it, so we have to come up with our own, and we always use that. This is less, so the decision would be reject a null. The null is that it equaled the the ratio. The ratios are 1 to 3 to 3 to 9. That was the claim. The ha is at least one ratio is different. All right. So the test gives sufficient evidence to reject. All right. And by the way, do we ever prove um, the claim? No, we never prove it. So it either didn't give or it did give. It'd be one of these two. This case we're rejecting, so our answer choice is D. All right. A sports fan conducted a test to investigate whether male high school athletes are equally divided among football, soccer, swimming, and tennis and basketball. So we have one, two, three, four, five categories. So that means we have five categories. I'm going to go ahead and write that down, five categories, because that might have to do something with my degrees of freedom. A sample of male high school students was selected, and the resulting chi-square test statistic was 10.65. Which of the following is the p-value? So they ran a chi-square test statistic, and they got a chi-squared value out here of 10.65. And they're looking for this area right here. They're looking for this shaded area. Well, this means I do need that categories. Degrees of freedom is categories minus one, so 5 minus 1 equals 4. If I go to second vars, I can see that I have a chi-squared CDF. All right, my lower bound, 10 points, oops, 10.65. This goes all the way to positive infinity. So we're just going to use 9 to the 99th. And my degrees of freedom is 5 minus 1, or 4. So I end up getting a p-value of about 0.030. All right. Best answer choice to 103 is B. Number 104. It is hypothesized that scores on a certain intelligence test are normally distributed with a mean of 100 and a standard deviation of 10. A psychologist runs a goodness of fit test on a simple random sample of 100 scores in the table. All right. Uh, what is the chi-squared statistic for this? All right. So if the mean is 100, all right, with a standard deviation of 10, let's draw a picture of this. Well, this is 100, all right? And we're going to go 90, and this right here would be 110. Well, I know that between 90 and 110 by empirical rule is 68%. So that means there should be 0.34% right here. All right. So there's 68% right here. And if I go 1 minus 0.68, I get 32%, but I have two tails, so I divide that in two, divided by 2. That tells me I need 16% here. This is 0.16, and this is 0.16. All right, so now I know those groups. So with that said, um, we can go, all right, let's do something really quick. Remember our formula. What's our formula for chi-squared? Chi-squared equals observed minus expected squared over expected. So let's make sure we have the observeds in the right spot. We should have 10, 40, 35, and 15 in the O spot. 10, 40, 35, and 15. 10, 40, 35, 15. 10, 40, 35, 15. 10, 40, 35, 15. Well, that didn't help. All right, so let's check so I need to calculate my expected. So I'm going to go ahead and act like I'm running the entire test, even though I'm not going to. So my observed values, 10, 40, 35, 15. My expected, well, I expect 16%. I expect 34%. I expect 34% and 16%. And at this point, I have 100 scores. So I'm going to go blue 2 times 100. And these are my expected values, 16, 34, 34, 16. All right, so my expected values match up here. That looks really good, but I need expected down here, and they put observed down there. 16, 34, 34, 6, and hey, it looks like we have a winner chicken dinner because I have my 16 here, 16 there, 34 here, 34 there, 34, 34, 16, 16, and my observed values match. So my answer to number 104 happens to be. All right, I'm going to pause this for a moment and I'll be back shortly. Good morning, this is your Stats Sensei, Mr. Spensei, and this is continuation of the Death Packet Problem 105. So, a major credit card company is investigating whether the distribution of the number of credit cards used by its customers has changed from last year to this year. Customers are classified as using one cards, two cards, or more than two cards. So that's kind of important. We have three classifications, so we have three categories. The company conducts a chi-square goodness of fit to investigate whether there's a change in the distribution of the number of cards used from last year to this year. The value of the chi-square test is 7.82 with the corresponding p-value of 0.02. And you can, by the way, you can check that out on calculator. I'm going to show you how to do that real quickly. Second vars, drop down to chi-squared. And we have a value of 7.82 going up to positive infinity. We have three categories, so 3 minus 1, and we should end up getting 0.02, which we do. Assuming the conditions for inference are met, which of the following is the correct interpretation of the p-value? Remember, p-value is the probability of getting a test statistic this extreme, so as extreme as 7.82, given that the null is true. So given that the null is true, there's a 2% chance of obtaining a chi-square value of at least 7.82 or more. All right? So 105 is C. That's just a straight up definition of p-value. 106, a chi-square goodness of fit test where all assumptions were met yielded the chi-square test statistic of 1.92 and a p-value of 0.05. The researcher interpreted the p-value as 0.7 probability of observing a test statistic of x equal to 1.92 or larger. What is wrong with the researcher's interpretation? The researcher's interpretation is really close, but p-value is the probability of getting a test statistic this extreme or more extreme given the null is true. And he did not say that given the null is true. So the problem with 106 is A, the researcher did not say that the p-value is the condition on the null hypothesis being true. All right. Remember, p-value, the probability of getting a test statistic this extreme or more extreme, given the null is true, or given the null is true, it's the probability of getting a test statistic this extreme or more extreme. All right. 107, a researcher is investigating and claims the proportion of television viewers who identify one of four shows as their favorite is the same for all four shows. All right. So if you have four shows, that means the probability 1 divided by 4 is 0.25. So everyone should be 25% if they're true, if it's really truly the same. A chi-square given as a fit test at a significance of 0.05 produced a chi-squared value of 8.95 with a corresponding p-value of 0.03. All right, so got to think about this real quickly because they told us what the null was. The null was that everything was equal. HO, the proportions are equal. All four proportions are equal, but I'm going to say proportions equal. Ha, at least one proportion is proportions equal 0.25. That's all proportions equal 0.25. At least one proportion is not equal to 0.25. All right, or is different than that. So we have a small p-value. We have a p-value of 0.03. They didn't tell us our alpha, but we're going to use 0.05 when they don't. 0.03 is less than that, so we're going to reject. So we're going to reject that they're the same and say that at least one is different. There is sufficient evidence to reject the null at the 0.05 level since the statistic is greater than the p-value. No, we're not looking at the test statistic. We're looking at the alpha value. All right, we're comparing it to the alpha. There is not sufficient. No, there is sufficient. There is sufficient evidence to reject the null hypothesis at the 0.05 level since the p-value is less than the significance level. Remember, significance level is another term for alpha. So the answer to 107 is C. All right, so that one's good. Moving on to 108. 2 commercial flights per day are made from a small county airport. The airport manager tabulates the number of on-time departures for a sample of 200 days. All right, so here's our observed values. What chi-square statistic for a goodness of fit that the distribution is binomial with a probability equal to 0.8 that a flight leaves on time? Wow, that just got really tricky. First off, let's deal with our formula and the observed values. Our formula is observed minus expected squared over the expected. Well, our observed are 12, 75, and 113. So we need 12, 75, and 113 in all of the observed spots. Well, okay, that worked out, so we didn't get to eliminate any. So we need to go back and think about a binomial. So we're going to need to run 3 different binomials. We're going to need, and we can either have 2, choose 0, 0.8 to the 0, 1 minus 0.8 squared. We can have 2, choose 1. One flight leaves on time. 1 minus 0.8 to the 2 minus 1, which is 1. Or we can have 2, choose 2, 0.8 squared times 1 minus 0.8 to the 0. So let's go ahead and run those. And second vars, binomial PDF. Now I can do it differently, but I'm going to do it as a PDF because it's going to be easy. Trials is 2. P is 0.8. X value is 0. So I get 0.04. All right, I'm going to run it again. Second vars, binomial, PDF, X value is 1. And we have 0.32. And this should be about 0.64. Second vars, binomial, PDF. And sure enough, it's 0.64. And the reason I knew that is it had to sum up to be a valid probability distribution. All right, so let's go ahead and act like we're running the entire test. So if I'm running the entire test, I'm putting my observed values in L1 and oops. And I'm going to put those percentages I just calculated in L2. So 0.04, 0.32 times 0.64. But I really don't need my percentages. I need my expected value, and expected value is essentially N times P. Well, we have our total was 200. They told us that. So I need to come up and multiply these values times 200. So blue 2 times 200, and I get 8, 64, and 128. So I need 8, 64, and 128. The only one that has the expected, see, this one has 8, 64, and 128, but these values down here, I don't know where they came from. They're wrong. The expected value, 8 and 8, 64 and 64, 128, and we already said these were our observed values. All right. So the answer to 108 happens to be A. Number 109. A chi-squared goodness of fit test used a significance level of alpha equal 0.05 was conducted to indicate whether the number of babies born in a town is uniformly distributed across the months of the year. All right, let's talk about uniformly distributed for a moment. Uniformly distributed means, oh, if I have all these bars, they're all the same height. Okay. Over the months of the year. Well, that means I should have 12 bars. So basically, I'm going to take 100% and divide it by 12. So I'm expecting each month to be 0.083. All right. The test produced a test statistic of 5.6 with a corresponding p-value of 0.9. Which of the following is correct? All right. So basically, the null is, in this case, it's uniform. The hot, I'm need to do this on separate again. All right, so in this case, our hoe is uniform. The ha is not uniform. And we ended up with a p-value of 0.90. They didn't give us an alpha, so we used 0.05. This is greater, so we're going to fail to reject. All right. We never proved the null. We just didn't reject it. Okay. So we are believing this because we failed to reject it. There was not sufficient evidence to reject it. All right. So we didn't prove it. We just said, oh, not enough evidence to suggest it. So I don't like this one because this said, oh, we proved it. We didn't. So I'm going to question that. It's possible, but I think it's wrong. There's sufficient evidence to suggest no, there wasn't. We did not reject. There is sufficient evidence to suggest it is uniform. We didn't prove that. We never do that. That's a wrong statement. There is not insufficient evidence to suggest the distribution of Earth is not uniformly. Yes, that is correct. That would be our p-value is 0.90, which is greater than our alpha. We failed to reject the null. There is not sufficient evidence to suggest the distribution of bursts is not uniform. Okay, so the answer to 109 is D. 110. Which of the following is not a condition for a chi-square goodness of fit? Data should be collected using a random sample or randomized experiment. By the way, that should always be the case. So that's we like that. We want this. This is a good thing. So that's not our answer. When sampling it without replacement, the sample size cannot be greater than 10% of the population. Oh, that's true. All expected counts should be greater than 5. Yep, that's true too. So the distribution of the sample should be approximately normal. No, the distribution of the sample is likely to be skewed. All right. But it doesn't really matter what the distribution of the sample is. We just need to have a sample expected counts greater than 5. When our expected counts are greater than 5, the distribution, it's large enough to use, it's large enough to proceed. All right. It becomes large enough to proceed. So normality does not come into play for the chi-squared. All right. The only time it comes into play for the chi-squared is if our degrees of freedom are 90 or more. And I don't think we ever run a test in AP statistics where the degrees of freedom are 90 or more. We usually have many fewer categories. We might have 20 categories, but we're not going to have 90. And without having that many categories, we can't be normal. All right. This concludes this video. Appreciate you watching. Look forward to seeing you on the next one. Thank you.